Section 3.2 Basic Differentiation Rules and Rates of Change. These are the objective. We're going to talk about how to find the derivative of constant function. We're going to talk about power rule, constant multiple rule, sum and difference rule. We're going to find derivative of sine and cosine function, exponential function, and eventually we're going to use derivative to find the rate of change. So first of all, constant rule. Let's say you have a constant function is called constant. For example, let me just give you f of x equal 5. It's a constant value. Here, this line, horizontal line, that represents the constant function, because wherever you go, the value of the function is same, that is c. So now, because the derivative is actually the rate of change, we would like to find the rate of change of this function. Since this is a constant function, there is no change, so the rate of change of this constant function would be 0. That's the whole point. Derivative means rate of change, and there is no change in constant function. That's why the derivative would be 0. So some of the examples, as you can see here, y equals 7 is a constant function, f of x equals 0 is a constant function, s of t equal -3. All these values on the right side, they are constant. There is no variable. Even here, k pi square, where k is constant and pi has a constant value, all these function, they are constant. So if we would like to find the derivative of this function, I'm using different notation here, dy over dx, f prime, s prime, dy over dx. But whatever you are using, whatever notation you're using, it doesn't matter. You are finding the derivative. Derivative is a rate of change, and rate of change of this constant function, all this constant function, is always 0. This is one of the very useful and important rule, that's called power rule. Let's say you have a function f of x is equal to x to the power n. X is the variable, n is some rational number. It could be actually this n could be any real number. Eventually you are going to we're going to use this for any real number, but for now, let's say n is a rational number here. Then the derivative of x to the power n is actually n times x to the power n minus 1. So let's say you are trying to find the derivative of x squared. Then according to this formula, the derivative or rate of change of this function x squared would be 2 times x times 2 minus 1, which is 1. So that's called power rule. You have to know this rule very well, okay? Some of the examples. Here you have 3 different functions, x to the power 3. This function can be written as x to the power 3 over 2. And this can be written as, always remember, to use the power rule, you should have x to the power some power here. If your x is on the denominator, then bring it on the numerator. And only after that you can apply the power rule. And if you use the power rule, these are the answer you're going to get. Look at here. 3 comes to the front times x, 3 minus 1 is 2. Here you have 1/3. So 1/3 comes to the front here, and 1/3 minus 1, 1/3 minus 1 is actually -2/3. Because it's a practice to show our final answer as a positive exponent, it's just a general trend. We bring this x to the power -2/3 on the denominator here. And here, the derivative of x to the power -2 is -2 from the formula times x to the power -2 -1, which gives you -3. But eventually, we want our answer in positive exponent form, so we have to bring this x to the power -3 on the denominator. Constant multiple rule. So let's say there is a constant and there is a function, and you would like to find the derivative of this type of expression. Then you can always bring this constant outside and multiply that by the derivative of the function inside. That's called constant multiple rule. Some of the examples. In the first example here, you are multiplying 5 times x cubed. The second example, it's a 2 times x to the power -1. And third one, it's a 4 over 5 t squared. So we are multiplying all these functions by some constant. So finding the derivative of this function is actually finding the derivative of this function times by this constant. So if you look at here, if you bring this 5 outside and then find the derivative of x cubed, which is by using the power rule, it's a 3 times x to the power 3 minus 1, which is 2. So 5 times 3 is 15 x squared. Now we can use the same trick here for the second expression and then third expression for finding the derivative. And that's possible because of this rule, constant multiple rule. Now we can, extend our power rule as the constant multiple rule and power rule together. So if you have c times x to the power n, then derivative of this expression is c times n times x to the power n minus 1. This is just the combination of constant rule and then power rule. The next rule is sum and difference rule. Let's say you have two different functions, f of x and g of x. Let's say both of them are the differentiable function, meaning you can find the derivative of those two functions. Then derivative of the sum of these two functions is actually sum of the derivative of corresponding function. So find the derivative of the first one, find the derivative of the second one separately, and just find the sum. And if you are looking for the difference, find the derivative of corresponding function and just find the difference between them. Example, let's say you have this function f of x, g of x, and y. By using the sum rule, finding the derivative of f of x means finding the derivative of the first function minus the second function plus the third function. And same here, you have to find the derivative of this corresponding function. There are separate functions at each term, and just use plus or minus between them. And that's only possible because of this sum and difference rule. So if you look at the answer here, the derivative of first expression is 3x squared. That's why it's a 3x squared. Minus is coming from there. The derivative of 4 times x is 4. Plus the derivative of 5 is 0. So you don't have to write 0 here. So very same idea. The derivative of x to the power 4, there is a negative sign. X to the power 4 is 4 times x to the power cube. And for the first one, it would be negative 4 times x cubed divided by 2. And if you divide 4 by 2, that's how you get negative 2. For the second one, it's a 3 times 3 comes from here. 3 times 3 is 9 times x squared. X squared is coming from the power rule. 3 minus 1 is 2. And minus the derivative of x is 1. So 2 times 1 is 2. Okay. Very same idea use here. Use the sum and difference rule and then power rule, and you can find the answer for the third expression as well. We can use the limit definition for finding the derivative of sine and cosine function, and eventually if you use the limit definition, this is what you are going to find. The derivative of sine function is cosine and derivative of cosine is negative sine. So these are very standard formula or the derivative. So I recommend you to remember this this formula. So by using these two formula, we can find the derivative of this expression. Now, what is the derivative of 2 sine x? It's a 2 times the derivative of sine x, which is cosine x. So if you use that fact here, so the derivative of this one is 2 times cosine x. The derivative of this one is half times cosine x. Derivative of this one is the derivative of x, which is 1, minus is coming from derivative of cosine x, because derivative of cosine x is negative sine x. Okay, eventually the derivative of cosine x is negative sine x minus pi over 3 is just a constant. Derivative of sine x is a cosine x. Derivative of the natural exponential function e to the power x is itself e to the power x. Some examples: the derivative of 3 times e to the power x would be 3 times e to the power x itself. The derivative of this one is 2x plus e to the power x. Derivative of this function, the last one, h of x, is derivative of sine x, which is cosine x minus e to the power x. So these are the answer. Now, rate of change. Rates of change. What is rates of change? The derivative is actually rates of change. If you are looking for rates of change of some function or some object, then actually you are looking for the derivative of that function. So the derivative can be used to determine the rate of change of one variable with respect to another. The meaning of that is, let's say you have y equal function of x. So your variable y changes as x changes. So we would like to find out how y changes as x changes. So that's called rate of change of y with respect to, another variable x. So we can use this rate of change idea or concept in our day-to-day life very frequently. For example, you are driving a car, you are going from one place to another place, so your distance is changing. So that's the derivative, that's the rate of change. As time passes, the population of a city could be going up or going down. It's changing. So we would like to find out what's the rate of change. That's actually derivative. So we can find this rate of change in a wide variety of fields. Okay, a common use of rate of change is to describe the motion of an object moving in a straight line. So something is moving like driving a car, and you would like to find the rate of change. Okay, for example, in this case, we can just plot our things in Cartesian coordinate system. Let's say this is the time, and this is the distance, and then something is changing like this, going from here to here. So we can find the rate of change, how this curve is changing. On such lines, movement to the right is considered to be in the positive direction, and to the left is considered to be the negative direction. Okay, so rate of change, eventually, let's say you have a position function s. S stands for the position function, and which is the function of time. S is function of time. As time passes, the position changes. Then we can find the rate of change of this position function by using this formula. So where is that? This one gives you the difference. Delta S means it's the small change in the position. So let's say something is moving on this curve going from here to here. So this notation delta S, it's actually the position change of this object from here to here. So in this case, it's a value of y coordinate. Okay, then the rate can be found by using this formula, which is distance over time. We always find the rate by dividing the distance by time, and then using the average velocity, we can find the average velocity, which is change in the distance, which is a small change in the position function divided by change in time. So that can be used, this expression can be used for finding the average velocity. So something is moving from here to here. This is time 1 and this is time 2. We would like to find out what is the average velocity. For that, we need to find out the change in distance, which is del S, over change in time, which is del T. These are the notation we use. That's actually the rate of change. Example, let's say you have a position function s, which is negative 16t squared plus 100. We would like to find out the average velocity on this interval, meaning from 1 second to the 2 second, how much the velocity will change. And same idea we can apply on this interval and on this interval. So let's look at here. For finding the average velocity change here, if we would like to use this formula, we want to find out delta S over delta T. On this interval, it's actually change in the position. So the value of the position at time 2 minus the value of the position at time 1 divided by change in time, which is 2 minus 1. So this is the expression we are looking for. So if you use this position function, which is s of t equal, that's given here, negative 16 t squared plus 100, and try to find this value s of 1. Just plug t equal to 1 here and put t equal to 2 here. That will give you these two values, 84 and 36. And using this formula, which is s2 minus s1 over t2 minus t1, you are going to find the value is negative 48. That's the average velocity. The average velocity is negative because, maybe it's going in the opposite direction or to the left side. Okay. Now, by using the same approach, we can find the average velocity on this interval or on this interval. It doesn't matter. It's the same formula, same idea. we can use to find the average velocity on any interval. Note that, this is one note I would like to mention here, note that the average velocities are negative, indicating that the object is moving downward. If instead of going up, if it's going down, then the average velocity would be negative. So now, if we try to find out the limiting value of this expression, which gives you the average velocity, if we try to find the limit of this, that's where we find the slope of the tangent line. That's what it represents, the rate of change. In our case, it represents the velocity. Instead of average velocity, it gives us velocity. So if you try to find the velocity, this is the expression we are looking for. Okay, the velocity function is the derivative of the position function. Velocity can be negative, 0 or positive. The speed of an object is the absolute value of its velocity. Speed cannot be negative. So if you are looking for the speed, find the velocity, make it positive. Okay, so that's the section 3.2.